Hi ladies and gentlemen. Now that we have got some basic introduction to Verilog, let us look at simple logic gates and simple logic circuits in Verilog. So let me start with that presentation. So the speech is organized into your learning outcomes, then Verilog modules for logic gates. Then we will see the old 3-bit prime detector we will redesign in Verilog. Then another simple logic function in Verilog and summary of what you learned. So what you will learn in this video is that you will create a Verilog modules and test benches for OR gate, NOR gate, NAND gate, NOT, XOR and XNOR gate. And already we have seen in the previous session. You will realize a 3-bit prime detector using Verilog. Then you will implement a simple logic circuit in Verilog. So the Verilog module for logic gates, we will see them one by one. Let us look at a NOT gate. So here module, N module, NOT gate is the name of the module, and here output, wire output is Y. There is one input and one output. The input is a wire, that is A, and the output is wire Y, so it is not Y comma A N module. This is very simple code. And the test benches, I already changed the old test bench, the one for AND gate. Only thing is I grave include NOT gate dot B, and module test bench register A, reg A, wire Y, and NOT gate, an instance of NOT gate is taken here. And other things are the same. Only thing is here I replaced A, B with Y and A alone. Here I dump into a file called notgate.bcd. Here I changed this, the stimuli has been changed. It is A equal to 1. When at 0 nanosecond, A equal to 0, and at 5 nanosecond, A equal to 1. So Y will be the complement of that. Let us run these codes and appreciate them. Let us look at them one by one. When this directories, these are there, let us look at the NOT gate. This is a notgate.v. So this is how it looks like. This is the one we saw just now. And let us run this code. I will enhance this a little. Okay. Here I will write Verilog. Verilog, what is the name? I will look at the names of the files. This is in NOT. Okay, I have these files here, NOT gate. Okay, now it is compiled without any error. Now let us look at this NOT TB, the test bench for NOT. Here you can see that this is a test bench which we saw now. Okay, and let us run this test bench. NOT tb dot v with some output file minus o some a dot out. Okay, and I run a dot out. You can see that when a equal to 0, y equal to 1, and when a equal to 1, y equal to 0. This VCD file can be opened with a GTK wave, so I invoke GTK wave here. GTK wave notgate.vcd. I have a notgate.vcd. Okay, GTK wave. you can see this name test bench is there. You can see that this register A is there, that is appended, where Y is appended. You can see that one is a complement of the other. Okay, here at 5 nanosecond it changes state from 0 to 1, so here it changes from high to low. So this is how it behaves. Other gates are also similar. I will look at some of the codes, like I'll go to say NAND. Okay, I have this NAND gate, which is nothing but NAND Y comma A comma B, and its test bench is NAND gate NAND TB. Very similar to this. Only thing is I included NAND gate dot V, and A and B are given. These things are just very identical with the others, with that AND gate. So here if I say, if I go to AND gate or NAND, I have these files here. I can run Verilog. Now it is compiled. Now I can run that test bench. I can specify some output file a.out. Okay, I can run this a.out. You can see that you can see the NAND behavior when it's 0 0. When one of the inputs is 0, output is a 1. So here it is A equal to 0, so output is 1. Here B equal to 0, output is 1. Here both are 1, so the output is a 0. So you can view the waveforms also. Here you have this test bench. You can see these things. These are my wire. Okay, I can append them here. You can see that here there is an AND behavior. When both the inputs are high, the output is a low. If one of the inputs is a low, output is a high. Here one of the inputs is low from up to 15 second. These values are one of the values is a low, so output is a high. Here both values at 15, both values become high, so output becomes a low. So in the same fashion you can analyze all gates. I will see you will see another gate, say XOR. Okay, XOR gate we will see. Here you have this XOR gate dot V. Just the XOR function, built-in XOR function is there. So here you can see the test bench. Here XOR gate is inserted. Other things are almost the same, just minor changes in that. And here I can run XOR. XOR gate dot V. Well, that runs, and I can run the test bench also. I can specify some output file. Okay, now I can run this a.out. You can see the XOR operation. When it is 0 0, output is a 0, or 0 1, output is a 1, 1 0, output is a 1, 1 1, output is a 0. Okay, this is the way my XOR circuit behave. I can see this file with GTK, with the VCD file. You can analyze these circuits, analyze these signals. I append all of them. Now you saw that when one of the inputs is a 1, output is a 1. Here it's a 0 1. When it is 0 0, when they are equal, output is a 0. When at 0 0 and 1 1, the output is a low. When one of the inputs when the inputs are different, 1 0 and 0 1 pattern, the output is a high. That this way you can analyze all circuits, all logic gates. So let me continue with this presentation. Now let us think about the old 3-bit prime detector. This we saw twice before, one with the algebraic reduction and with the K-map reduction. We designed this so that function is y is a complement and b or a and c. So this is the way the circuit looks like. Now here these ABC are wires. Now we are going to implement it in Verilog. So these ABC are wires. Y is also a wire. But there are some internal nets here, x1, x2, x3. Okay, so when I write this module, I write module, say prime detector name, output is wire Y and input wire ABC. Now there are 3 other wires also. They are internal nets. They do not come as an input or output. They are inside the circuit, so they are declared later than this. After this header here, wire x1, x2, x3. After this port declaration, not a header but a port declaration, here these wires are declared, wire x1, x2, x3. Okay, now I compute this x1. X1 is nothing but this is a NOT operation. First A is inverted. So here it is NOT, say N1, and that is the name of the gate, x1 comma A. That gives this inversion, that gets my x1. X1 is a complement. This statement says that x1 is a complement. Now what next? That should be, this x1 should be ANDed with my B, so that I get my x2. So x2 is, this is an AND operation, x2 is the output, B and x1 are the inputs, x1 is the internal net. Okay. Then I have another AND gate here. This is x3, output is x3, which is nothing but AC, I'm sorry, A comma C, x3. This statement says that x3 is A and C. Now I have the last connection, that is x2 or x3, that comes here, or x2 or x3, that is my output Y, that is a wire Y. Okay, and N module. Now you can have a test bench for that, but rather than saying here, I will show you in the text editor. That will be more pleasing. I have my prime detector .v, and I have my prime detector TB. Okay, this is my prime detector. This I already discussed. And if you look at the diagram, this will be very clear. Now here I have a prime detector TB. Okay, what it does is it includes the prime detector V, and this module test bench, some name can be given. Here I have this reg ABC and wire Y. So an instance of prime detector is applied here. Okay, then other things are the same. Here ABC inputs are there. Then I dump into a file prime detector.vcd. Now here I give all possible patterns manually, like 000, 001, 010, 011, 100, 101, 110, and 111. Okay, then I finish this and end module. Now if I run this, first I have to run this prime detector.v. Similar to this, I Verilog prime, not an X or this outside this. That is compiled. Now I will look into this prime detector TB. -O A dot out. Okay, here I slide A dot out. Now you can see that here, when initially at 0 this 0th time, this A and B, ABC are indeterminate, so Y is indeterminate. Normally we have an initial reset. Okay, we will have a global reset happening initially, so such a conditions do not occur practically, but here it is 0 0 0, it is 0 0 0 1, it's a 0, then 0 1 0 for 3 0 and 1 are not primes, 2 is a prime, 0 1 0, then it's a 0 1 1 is again a prime. You can see that 1 0 0 is not a prime, then 1 0 1 it's a prime, that is 5, then 1 1 0 is not a prime, then the last one, when 1 1 1 comes, y is equal to 1, indicating that it is a prime. You can show the waveforms also. Here I see where is a waveform, that is a prime detector dot vcd. You can take this all these signals and you can append them. Here you can see that I will zoom it a little. Here it is intermittent for a few seconds. Here there may be a global reset happening here, so this conditions do not practically occur. Here if you come here at 0 1 0 and 0 1 1 it is high, then at 1 0 1 1 0 1 it is high, then at 1 1 1 my output is high. So this is how I develop my prime detector in Verilog. Now let me go back to the presentation. Now we have seen another simple function here, sigma m135, sigma m135. So that is we established by ChemUp that f equal to a complement c or b complement c, or what do you call ab complement ab and so. But here it is ab and all complement and c, n and b and c. So this is a circuit. So here the inputs are a b c, these are wires, and the output is y, that's a wire, and there is an internal net x. So my circuit look like this. My Verilog code looks like this. Some module, some another circuit, some name, output wire y, input wire ABC, and there's an internal net that is y, wire that is x. I say NAND a comma b. What is this x? That is a NAND b. X is a NAND b, and the last one, this is ANDed with a c. Okay, this is ANDed with a c, this AX is ANDed with a c. Okay, so AND module. The test bench looks like this. We will run this code. I have something called another circuit.v. I Verilog .v. Now I will run the test bench. I will specify some output file a.out. Okay, you can run this a.out. It is for 135, so you can see that this is 0 0 0, it is 0 0 0 1, that is corresponding to 1, y is 1. Then I have a 0 1 0 0 0 1 1, that is 3, that is a 1, y is 1, output is 1. Then 1 0 0 output is 0, 1 0 1 output is 1, 1 1 0 output is 0, 1 1 1 again output is 0. We can see this waveform with the GTK wave. You can analyze the signals with the GTK wave. Another circuit.vcd, GTK wave, another circuit.vcd. Here you can set for 1, that is 0 0 1, it is a 1. Then 0 1 0 0 1 1, that is 3, it is a high. Then for 1 0 1 1 0 1, it is a 1, everywhere else it is 0. So it is a 1 sigma m135. Okay. Now coming to the end, what you understood in this video is that you learn to create Verilog modules and test benches for OR, NOR, NOT, NAND, etc. Gates, simple gates. It's very easy. You know one gate and you can change it, and you can create any other gate. Then you realize that the 3-bit prime detector using Verilog. Then you implemented a simple logic circuit in Verilog. And that's the end of this video. Thank you.